welcome to two projects. In this video, we are going to explain the project Multi-class classification of plant leaf diseases using feature fusion of deep convolutional neural network and local binary pattern. Introduction. So, this project revolves around leveraging deep learning, specifically a deep convolutional neural network that is DCNN, to enhance the early detection and classification of plant diseases. Traditional methods reliant on expert visual examination are costly and inefficient, prompting the need for a more advanced and automated approach. Precision agriculture success hinges on timely disease identification to minimize crop losses. By integrating AI, the project aims to surpass the limitations of conventional methods, ensuring a cost effective and efficient means of disease detection in plant leaves. Acknowledging drawbacks in existing techniques, the project proposes a novel DCNN model replacing traditional convolutional layers with deeper separable convolutions. This modification reduces model parameters and iteration time, addressing computational challenges. And the integration of deep features with local binary patterns defines the model's ability to capture both global and local characteristics. So, the project's methodology combines advanced AI with handcrafted features for improved plant disease classification. The beneficiaries include farmers, agricultural experts, and the global population, promising more accurate and timely disease identification for increased crop yield and food security. Objective of the project. So, as I mentioned earlier, the primary objective of the project is to implement and evaluate diverse deep learning models, CNN with LBP, DCNN, VGG16, GoogleNet, LXNet, and Exception, to systematically compare their performance in plant disease identification. And the goal is to identify the most effective model, enhancing accuracy and operational efficiency in precision agriculture. And we aim to establish a cost effective and automated approach to plant disease classification, reducing reliance on expert driven methods. This will empower precision agriculture with timely and accurate disease detection, minimizing crop losses. And the goal is to contribute to global food security by providing farmers and agricultural experts with state of the art tools for precise and timely identification of plant diseases. The project aims to optimize crop yield and enhance agricultural sustainability on a broader scale. Requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Back-end framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working models of law of work. So the first step is import and required packages. So we begin by importing essential packages such as NumPy, Pandas, sklearn, Matplotlib, TensorFlow, and Keras to facilitate data handling, visualization, and deep learning model development. The second step is exploring the dataset. So, the dataset sourced from Plant Village and RoboFlow encompasses images of apple, tomato, and grape leaves. Exploratory analysis ensures a comprehensive understanding of the data, a crucial step in model development. The third step is image pre-processing. So, by utilizing image data generator, images undergo pre-processing steps including descaling, shear transformation, zooming, horizontal flip, and reshaping in this step. Feature extraction, particularly local binary pattern that is LBP, enhances the model's ability to discern intricate patterns in leaf images. Additionally, torch vision aids in dataset processing for detection models. The next step is training and building the model. So here, various classification models are trained and built, including convolutional neural network that is CNN with LBP feature extraction, deep convolutional neural network, VGG16, GoogleNet, and LXNet. These models aim to efficiently classify plant diseases based on input images. And in the next step, as an extension, we built detection models using YOLO versions 5 to 8. YOLO, that is, you only look once models, enable simultaneous object detection and classification, enhancing the project scope for identifying plant diseases in images. Additionally, we have built a exception model for classification tasks. And the project extends its functionality by developing a user friendly front end interface using the Flask framework. So, the inclusion of user authentication features powered by SQLite ensures a secure and personalized experience for users during testing and analysis. So, after signing in, users are facilitated to upload images for analysis through the front end interface. The input images undergo pre processing steps ensuring compatibility with the trained models and setting the stage for accurate recognition. The diverse set of trained models encompassing various architectures collaborates to provide accurate recognition and classification of plant diseases. And the project concludes by presenting the final analysis outcome to the user through the front end interface. Results are displayed in a user friendly manner, showcasing the effectiveness of the models in recognizing and categorizing plant diseases. Now we'll understand about the algorithms used. So the first algorithm built is CNN with LBP feature extraction. So convolutional neural network CNNs are deep learning models designed for image classification. In this project, a CNN is enhanced with local binary pattern, that is LBP feature extraction. CNNs learn hierarchical representations of image features through convolutional layers, pooling layers, and fully connected layers. The inclusion of LBP, a texture descriptor, further refines feature extraction by capturing local patterns, contributing to more robust disease identification in plant leaves. The next algorithm built is DCNN, that is Deep Convolutional Neural Network. So, a deep convolutional neural network extends the capabilities of a traditional CNN by employing deeper and more complex architectures. DCNNs often use separable convolutions to reduce the number of parameters and computational load. In this project, DCNN is applied to improve the efficiency of feature learning and enhance the model's ability to classify plant diseases accurately. The next one is VGG16. So VGG16, short for Visual Geometry Group 16, is a widely used CNN architecture known for its simplicity and effectiveness. It consists of 16 convolutional and fully connected layers utilizing small 3 by 3 convolutional filters. In this project, VGG16 is employed for its proven performance in image classification tasks, providing a balance between model complexity and accuracy for identifying various plant leaf diseases. The next algorithm built is GoogleNet. So, GoogleNet, also known as Inception V1, introduces the concept of inception modules. These modules use parallel convolutional operations with different filter sizes to capture features at various scales. This architecture helps mitigate the vanishing gradient problem and enables efficient learning of complex patterns. In the project, GoogleNet is chosen for its ability to handle diverse plant leaf disease patterns, enhancing classification accuracy. And the next one is LXNet. So, LXNet is a seminal CNN architecture known for its success in the ImageNet large scale visual recognition challenge. It consists of 5 convolutional layers followed by 3 fully connected layers. LXNet employs techniques such as ReLU activation, dropout, and local response normalization for effective feature learning. In this project, LXNet is utilized for its capacity to capture hierarchical features, contributing to accurate plant disease classification. Now we'll see the comparison graphs of the algorithms built for classification of apple leaf diseases. So this is the horizontal bar graph comparing accuracy scores of different algorithms. In this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. Accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. This is precision scores comparison graph. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. Precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall scores comparison graph. In this graph, on x-axis I have recall scores and on y-axis I have algorithm names. Recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F1 scores comparison graph. In this graph, on x-axis I have F1 scores and on y-axis I have algorithm names. F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for classifications. So these are the comparison graphs of the algorithms built for classification of grape leaf diseases. Similarly, these are the comparison graphs of the algorithms built for classification of tomato leaf diseases. So now we'll see the comparison graphs of the algorithms built for detection of apple leaf diseases. So this is the horizontal bar graph comparing precision scores of different algorithms. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions, representing the ratio of true positives to the sum of true positives and false positives. And this is recall scores comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. So recall assesses the model's ability to capture relevant instances, calculated as the ratio of true positives to true positives and false negatives. And this is MAP scores comparison graph. In this graph on x-axis I have MAP, that is mean average precision scores, and on y-axis I have algorithm names. So MAP evaluates object detection performance by calculating the average precision for each class and then determining the mean over all classes. So the algorithm which is best performing in all the performance metrics will be used for detections. So these are the comparison graphs of the algorithms built for detection of grape leaf diseases. Similarly, these are the comparison graphs of the algorithms built for detection of tomato leaf diseases. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So in these folders, I have the required dataset for classification task. So I have dataset with class labels on which we will train the models. This is the detection folder in which I have required dataset for detection task, and I have code built for detection task here. And this is sample folder in which I have images on which we will make the classifications and detections. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. These are Jupyter source files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. So this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on sign up button to register. And if we already have account, we can directly log in by clicking on this link. So as I already have account, I'm clicking on this link. So here we have to provide a credentials, username and password and click on sign in button. So it has redirected us to the detection page. So as I mentioned earlier, we can perform both classification and detection tasks in this project. So first we'll perform the classification task. Click on classification link. So we can perform the classification task on three different data sets: grape, apple and tomato. First we'll classify the grape leaf diseases. Click on grape link. So here we have to upload any grape leaf image and the application will classify the disease from the image. Click on choose file button. So I'm uploading this image and click on open. The image is loaded. Now click on upload button. So here this is the uploaded image and here we can see the classification, that is gray black measles. We'll try again. Click on try again link. We'll try giving another image. Click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. This is the uploaded image and here we can see the prediction, that is grape black rot. So the grape disease has been classified as grape black rot. Click on try again link. Click on choose file button. This time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So for this image, it has classified it as grape healthy. So similarly, we can upload any image and can get the classifications. Click on classification link. So this time we'll give Apple images. Click on Apple link. We'll try classifying the Apple images. Click on choose file button. So from Apple folder, from classification subfolder, I'm giving the Apple leaf images. I'm giving this image and click on open. The image is loaded. Now click on upload button. This is the uploaded image and here we can see the prediction, that is Apple black rot. Click on try again link. Click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So for this uploaded image, it has classified the disease as Apple black rot again. We'll try again. Click on try again link. Click on choose file button. This time I'm giving this image and click on open. The image is loaded. Now click on upload button. This is the uploaded image and here we can see the disease classification, that is apple scab. Similarly, we can upload any apple leaf image and can get the classification of the diseases. Click on classification link. This time we'll try with tomato leaf images. Click on tomato link. Click on choose file button. So I'm uploading this image and click on open. The image is loaded. Now click on upload button. This is the uploaded image and here we can see the classification, that is tomato early blight. We'll try giving another image. Click on try again link. Click on choose file button. So this time I'm uploading this one and click on open. Click on upload button. This is the uploaded image and here we can see the classification, that is tomato septoria leaf spot. Similarly, we can upload any image and can get the classifications. This time I'm giving this image and click on open. The image is loaded. Now click on upload button. So for this image, it has classified it as tomato healthy. Now we'll perform the detection task. Click on detection link. So we'll perform the detection on grape leaves. Click on grape link. Click on choose file button. So from grape folder, from detection subfolder, I'm selecting this image and click on open. The image is loaded. Now click on upload button. So here we can see the application has detected the grape leaf disease. It has drawn a bounding box around the disease leaf. And here we can see the classification also, that is black measles. So it has classified this grape leaf disease as black measles. And we can also see a probability score here telling us how confident the application is about the detection. Click on back. We'll try again. Click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So we can see it has detected the leaf. It has drawn a bounding box around the leaf. And we can see the classification also, that is healthy leaf. And we can also see a probability score telling us the confidence level of the detection. Click on back. Click on detection link. Now we'll try giving apple leaf. Click on apple link. Click on choose file button. So I'm giving this image and click on open. The image is loaded. Now click on upload button. So here we can see the application has detected the apple leaf disease. It has drawn a bounding box around that and it has classified it as healthy leaf. And we can see a probability score here telling us how confident the application is about the detection. So the application has detected this leaf as healthy leaf. Click on back. Click on choose file button. So I'm uploading this image and click on open. The image is loaded. Now click on upload button. We can see the detection. It has detected the leaf. It has drawn a bounding box around the leaf. And we can see the classification and the probability score. Click on back. Now we'll detect the diseases in tomato leaves. Click on tomato link. So click on choose file button. So I'm uploading this leaf and click on open. The image is loaded. Now click on upload button. So here we can see the application has detected the leaf, the diseased leaf. It has drawn a bounding box around the diseased leaf. And we can see the classification also, that is mosaic virus, and we can see the probability score. Click on back. Similarly, we can upload any image and can get the detections. Now click on sign out. So the conclusion here is the project successfully implemented and evaluated diverse deep learning models including CNN with LBP, DCNN, VGG16, GoogleNet, and AlexNet. Through systematic comparison, insights into their effectiveness for plant disease identification were gained. The establishment of a cost effective and automated plant disease classification system reduces reliance on expert driven methods. This technological advancement empowers precision agriculture with timely and accurate disease detection, minimizing crop losses. And by providing state of the art tools for precise and timely identification of plant diseases, the project contributes to global food security. The optimized crop yield and enhanced agricultural sustainability achieved through these advancements benefit farmers and the broader population. And the project extended its scope by incorporating exception model for classification and YOLO versions 5 to 8 for detection models. These additions enhance the project's capabilities, allowing simultaneous object detection and classification, further improving plant disease identification in images. And as an extension, the project integrated a front end using Flask with SQLite for user authentication. This user friendly interface allows users to input images which undergo pre processing. The trained models then perform both classification and detection, and the final outcomes are presented through the front end, facilitating practical and accessible user testing. Overall, the project's innovative approach and comprehensive solutions contribute significantly to the field of precision agriculture and plant disease management.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.